Welcome back to the Deep Dive. Today we are tackling what is arguably the biggest bottleneck right now in generalist robotics.
Yeah, it's a big one. We've got these incredible vision language action models, VLAs, that are fantastic at following instructions.
But they've been stuck. They're almost all attached to these, simple pincers, just 2 or 3 finger grippers.
Exactly. And if the real goal is human-level manipulation, that's just not going to cut it. You need dexterous hands. High degrees of freedom hands.
We're talking about a huge leap in complexity here.
Oh, it's exponential. You go from a few joints to dozens. The control space explodes, you get constant occlusion problems, and the cost of collecting data is just, oh, it's astronomical.
Which brings us to today's source. We have a technical report from ByteDance that claims to have a solution, GR-Dexter.
That's right. They're proposing a whole framework, hardware, model, and data all working together.
So our mission for this deep dive is to unpack exactly how GR-Dexter scales these VLA policies to get this, a 56 DUF bimanual robot system.
56, it's an incredible number.
Okay, let's start at the foundation, the hardware. What are they building on?
So the core of it is their new hand, the ByteDexter V2. It's really engineered for this. It's compact, it's anthropomorphic, so it looks a lot like a human hand.
And it's not just about looks.
Not at all. It uses this really ingenious linkage-driven system. And crucially, each hand packs 21 degrees of freedom.
21 per hand, wow.
Yeah. The thumb alone has 5, and then each of the 4 fingers has 4.
So that's how they get to such a high number. They're not just tacking them onto any old robot arm.
No, they're deploying 2 of these V2 hands on a dual-arm platform, specifically 2 Franca Research 3 arms. You add up the arm and the hand duffs, and that's how you hit that headline number, 56 duff.
Built for two-handed tasks from the ground up.
Precisely. And what's really fascinating is they've integrated these high-density piezoresistive tactile sensors right into the fingertips.
So it has a sense of touch.
It has a sense of touch, yeah.
Yeah.
Crucial for delicate work. They report it can pull off all 33 of the FAEX grasp types, which is basically the entire dictionary of human grasping.
Okay, a 56 DUF system is just staggering. I mean, that's more joints than a human has in both their arms and hands. How on earth do you train something like that without needing infinite data?
That is the million-dollar question. And this is where their real innovation comes in, I think. It's what they call their data pyramid.
A data pyramid. Okay, break that down for me.
It's a multi-layered strategy. So at the very top, the most valuable, most specific data, you have teleoperated robot trajectories.
So a human is driving the robot.
Right, but they made it super efficient. They use a custom VR setup, a MetaQuest headset, and Manus gloves, which lets them retarget human motion in real time. This is how they got demonstrations of incredibly complex tasks. We're talking knitting, writing calligraphy.
Wow. Okay, so that's the super high quality layer. What's underneath that?
Well, to get generalization, they need more. The next layer is just massive web-scale vision language data. This is just to train the VLM backbone so it understands language.
Makes sense.
Then they pull in cross-embodiment data. So they're using existing data sets from other robots, like the Open Loon Baihu. They're not reinventing the wheel.
And the base of the pyramid.
The base is over 800 hours of egocentric human trajectories, human videos. Now, they have to filter this data really carefully and retarget it because of the kinematic gap, the physical differences between a human hand and the robot hand.
So let's talk payoff. What can this whole system actually do?
This is where it gets really impressive. It excels at these long horizon everyday tasks. The report gives examples like bread solving with tongs. One hand uses the tongs, the other holds the plate.
Real coordination.
Exactly. Or vacuum handle, grasp and sweep, where it has to coordinate a 4-finger grasp while the thumb is busy pressing the power button.
That's quite specific. But what about generalization? When you throw it a curveball?
That's the biggest breakthrough. They tested a makeup decluttering task. Now, when faced with a table layout it had never seen before, what they call out of distribution, a plain VLA baseline model, its success rate dropped to 0.64.
Which is not great.
Not great. But GR-Dexter, with its data pyramid, its success rate jumped to 0.89.
That's a huge leap. That shows it's actually learning the underlying task, not just memorizing layouts.
It's robust generalization. And because of that deep VL data, it can follow really abstract commands, things like pick up the darkest object or even pick up the drinkable object.
So tying this all together, what's the big picture here?
I mean, GR-Dexter really proves that VLA policies can be scaled to these super high-def dexterous systems. The key insight is you can't just have one piece. You need the novel hardware, the simplified teleoperation, and this really clever multi-layered data mix to beat that complexity barrier.
A really profound step forward. But, the authors themselves noted a limitation. The hand and arm are still controlled as separate parts, which can hinder that super tight coordination.
Yeah, there's still a bit of a disconnect there.
So here's a thought for you to chew on. What if the next step is a single, unified model that controls the entire 56 DOF system as one integrated unit? What would that kind of seamless control unlock for, say, general assistance in our homes? Something to think about until our next deep dive.